Hello. In the last lecture, we have seen the definition of curvature of a regular curve. In this lecture, we will be computing the curvature of a curve. So in order to do that thing, so we'll be finding a formula how to find a curvature of a regular curve, which is sitting inside R2 or in R3. Okay, so let us begin with the definition of curvature of a regular curve, so that we have defined in the last class. So let us take a regular curve alpha in Rn. So in order to define curvature of alpha, so we should reparameterize alpha such that the new reparameterization, it will be unit reparameterization. So let alpha tilde be a unit reparameterization of alpha, or also you can take this alpha tilde to be arc length reparameterization of alpha. So alpha tilde be an arc length reparameterization of alpha. So we have taken arc length reparameterization. So this is also an unit speed reparameterization of alpha. And now, so suppose this alpha tilde is defined on this interval a tilde b tilde to Rn, and let S be the arc length parameter. So then how do you compute the curvature? So then the curvature of alpha at alpha tilde S is given by norm of alpha tilde double prime S. So you take the unit speed reparameterization of this alpha, and you take the double derivative and take its norm. So that will give you the curvature of alpha at alpha tilde S. Okay. So note that, so suppose this is my curve alpha, and I have taken a unit speed reparameterization. So here I have taken arc length reparameterization. So again, so the image of alpha or trace of alpha, so trace of alpha is same as trace of alpha tilde. So if this is my alpha A and this is my, say, alpha B, so alpha A is same as alpha tilde A tilde, and this is equal to again alpha tilde B tilde. So if I take any point on alpha, so this can be also taken as alpha tilde S. Okay, all right. So this was the definition of curvature of alpha at alpha tilde S. S. Okay. So now we are going to find a formula for curvature of a curve in R3. Okay, so before that, so let me recall this few things which you have done earlier. So what is cross product or vector product? So let us take two vectors, A bar and B bar in R3. So this A bar, so you can write in terms of its coordinate as follows. So A bar is A1, A2, A3, which has another representation, A1, I bar, A2, J bar, A3, K bar. Okay, so this I bar represents the unit vector 1, 0, 0. J bar, it represents the unit vector 0, 1, 0. And this K bar, it represents the unit vector 0, 0, 1. So similarly, I can write this B bar as B1 I bar, B2 J bar, and B3 K bar. So now, what is the vector product of A with B? So it is denoted by A cross B. So it is the determinant of the following matrix. So which is equal to A2 B3 minus A2 B1 plus B1 A3 minus A1 B3 J bar plus A1 B2 minus A2 B1 K bar. Okay, so this is the definition of cross product. So also, so we have the following entity. So this you can show. So take three vectors now and take the following vector product. So first you take B vector product with C, and then after that you take A vector product with B and C. So this will be equal to dot product of A with C, the scalar multiplier. So A dot product of A with C is a scalar. So then you multiply it with the vector B bar minus this dot product A with B, and then you have the C bar. Okay. So now, so let us take a regular curve in R3. So proposition. So gamma t be a regular curve in R3. So here I'm not writing the domain of this gamma. So t is varying in some open interval. Okay, so then its curvature is given as follows. So then the curvature of gamma at gamma t is given by kt equal to norm of gamma double prime t cross product with gamma prime t. Yeah. So in the numerator, you have the this norm divided by norm of gamma prime t whole cube. Okay, so this we are going to show. So this curvature is given by this formula. Okay, so also note that, so we'll be using this notation sometime. So gamma dot t, it means the velocity vector. So this is just gamma prime t, gamma double dot t, it is this acceleration vector, gamma double prime t. Alright, okay. So now let me try to prove this thing. So let us take, so let S be the arc length parameter of alpha. Okay. So therefore, this ST, so it is nothing but, sorry, here the curve, I have taken it to be gamma. So S be the arc length parameter of this gamma. So ST, it is ds dt is nothing but equal to norm of this gamma dot t. Okay, all right. So this gamma dot t, it is the differentiation of gamma with respect to t at gamma t. So this is also I can write, so d gamma s times ds dt. So this always we can write, and this curvature, so kt, so it is equal to norm of this gamma double prime s or gamma double dot s, so which is again equal to norm of d2 gamma ds2. So this again I can write as follows. It is the norm of dds of d gamma ds. So this again is equal to this. So note that, so this s parameter, it is a function of t. So in fact, it is differentiable, and S inverse also exists, that is also differentiable. Yes, so we have this thing. Okay, so now, so this can be again written as follows. Yeah, so which is again equal to, so norm of ddt of gamma dot t d2 gamma dot t divided by ds dt divided by norm of ds dt. Okay, so now if I take this differentiation, so it is gamma dot t by ds dt, so which is again equal to as follows. It is norm of dst dt gamma double dot t minus d2s dt2 gamma dot t and close the norm. And in the denominator, so what you have, norm of ds dt multiplied by norm of ds dt whole square. Okay. So now, so this ds dt whole square is nothing but inner product of this gamma dot t with gamma dot t. Okay, so let me do it. So ds dt is norm of gamma prime t. So now if I take the square, so it will be equal to square of the norm of gamma dot t. So which is again equal to dot product of these two tangent vector. Okay. So now if I take the derivative here, so what we'll get? So 2 ds dt d2s dt2. So it is equal to twice gamma double prime t dot gamma dot t. So you'll get this thing. So this implies that, so this 2 it will cancel. So what we have now, ds dt multiplied by d2s dt2 is equal to the dot product of the acceleration vector and the velocity vector. Okay, so now from this equation star, so from equation star, so what we have, this curvature k at t, so this is equal to norm of so let me again rewrite the thing here. Okay, so here what I can do, so I can multiply the numerator and denominator in this equation by ds dt. So if I do this thing, so what we'll have, so ds dt whole square times gamma double dot t minus d2s dt2 ds dt times gamma dot t, close the norm. So divided by this ds dt to the power 4. So we have this thing here. So now in the numerator, by this previous identity, so what we have, so this is equal to norm of gamma dot t dot product. So you have this dot product times gamma double prime double dot t minus gamma double dot t dot product with gamma dot t times this velocity vector gamma dot t. Close the norm. So divided by, so ds dt is norm of gamma dot t. So you have this thing. Okay. So therefore in the numerator, So what do we have? So this gamma dot t. So this vector, take the vector product with this vector product. Okay. So the curvature is now is equal to this thing. Okay. So now note that. So this gamma dot t. So this tangent vector is orthogonal to or perpendicular to this vector. Okay. So what we know that, so norm of A cross B is equal to norm A times norm B sine theta, where theta is the angle between A and B. So here theta is equal to pi by 2. So therefore what we have, so this is equal to your norm of gamma dot t times norm of this vector product divided by norm of gamma dot t to the power 4. So therefore, so we have this required formula. Okay, so we have obtained this formula for a regular curve in R3. Okay, so now suppose you are given a curve which lies in a plane. So how to find a curvature of that? So this is a corollary of this proposition. So let us take a curve. So let alpha t equal to xt yt be a regular curve in R2. Okay, so let this be a regular curve in R2. So then the curvature of alpha at alpha t is given by kt equal to mod of this x prime t multiplied by y prime t minus x double prime t multiplied by y prime t divided by this quantity. So x prime t square plus y prime t square whole to the power 3 by 2. Okay. So now let us try to show this thing. So how we will get. So this planar curve, you can think it also lies in R3. So let us take, so let gamma t to be equal to xt comma yt comma 0. Okay. So this is the picture. So this is my xy plane and the curve is lying in this xy plane. So this curve, it is lying in xy plane. So this I can think also in R3. So the curvature of this alpha, it will remain the same. So the curvature of gamma is same as curvature of alpha. Okay. So therefore, so this kt, so by our formula, so this is equal to norm of this gamma dot t vector product with gamma double dot t divided by norm of this gamma dot t q. Okay. And so what is my gamma dot t? So this is x prime t, y prime t, comma 0, and gamma double prime t is x double prime t, y double prime t, comma 0. And now if I take the vector product, so this will be equal to, so this scalar, so x prime t, y double prime t minus x double prime t, y prime t times the unit vector k bar. Okay. So therefore the curvature, so this is given to be so equal to norm of this this vector product, so which is nothing but the mod of this x prime t, y double prime t minus x double prime t multiplied by y prime t. So divided by uh, take the norm of gamma dot t and take the cube. So what is gamma dot t? It is root over x prime t square plus y prime t square. So therefore, so what we have, so this is x prime t square plus y prime t square to the power 3 by 2. Okay. So in this way, so we get the curvature of this planar curve. Okay. So now suppose you were given a curve in the form of graph. So let me write down this thing. So f be a smooth function. So it means that this f is differentiable, and so all the derivatives of f exist up to desired order. So f, it is a real valued function. So I can take the graph of this f. So graph of f is this thing. So x comma fx, where this x, it belongs to your interval a b. So this, I can draw a diagram here. So this is the graph of this f. Okay. So this graph I can parameterize as follows. So let alpha t is equal to t comma ft. So again, this t, it is varying in this interval a b. Okay. So now what is my alpha dot t is equal to 1 comma f prime t. Okay. So this is never 0 because the first coordinate is 1. So this alpha, so this implies this alpha is a regular curve. So this alpha, it is a regular curve. And so what will be the curvature of this alpha? Okay. So here note that this xt is equal to t and yt is equal to the function ft. Okay. So if I compute this thing, so this xt is equal to 1, xt is equal to t. So this x prime t here, it will be equal to 1. And y double prime t, it will be equal to f double prime t. And this expression, because xt is equal to t, so x double prime t will be equal to 0. So this expression will be 0. Okay. So therefore, so the curvature, so this will be equal to mod of f double prime t divided by 1 plus f prime t square whole to the power 3 by 2. Okay. So this is the curvature of alpha at alpha t. All right. So now let us first do some examples. So examples. So first let us take a straight line. So let us take, so this gamma t to be this straight line. So this gamma is a straight line. So I can take this t in Rn. So gamma is a straight line. So with direction ratio to be your p. So I can compute the velocity vector, which will be here, it is constant. Okay. And so this straight line, it can be in Rn also. Okay, so t it varies in Rn, so then we'll get a straight line in Rn. All right. Okay. So now, so what will be the arc length parameter? So you take this integration 0 to t norm of this gamma dot t dt. So it will be equal to your norm of p bar times t. Okay, so therefore this t, so this will be given as follows. So here obviously, so this p bar is not equal to the 0 vector. So t is equal to 1 by norm of this p times your s. So s is the arc length parameter. So gamma tilde s, so gamma tilde is the arc length reparametration of the straight line gamma. So this is given as follows. So p bar by norm of this p times s plus q. Okay. And now you take the double derivative of this gamma tilde with respect to s, and this is always 0. So this means that the curvature of any straight line is 0. Okay. So now let us take another curve in R3. So let us take, so this gamma t to be your cos t, sin t, comma t. Okay. And so you can compute the velocity vector. So this gamma dot t, so this is equal to your minus sin t, cos t, 1. So now you can use that formula. So gamma double dot t is equal to minus cos t minus sin t, comma 0. And uh, this vector product, so you can compute. So this will be equal to minus sin t times the unit vector I plus cos t times the unit vector j bar minus this unit vector k bar. Yeah. So this kt, so this will be given as follows. So it is the norm of this gamma double prime t cross product with gamma dot t divided by norm of this gamma dot t whole cube. Yeah. So here, so this will be in the numerator norm of this vector product. So this will be minus sin t square plus cos t square plus minus 1 square. So divided by root of, so minus sin t square plus cos t square plus 1 to the power cube. So what we have? So in the numerator, we have root 2 divided by root 2 cube. So this kt, so this will be equal to your half. Okay. All right. So similarly, so you can compute the curvature of this planar curve. So let gamma t is equal to t square t cube. So here, so this t I have to take, it is greater than 0. So t is greater than 0 because if I take t equals to 0, so gamma dot t at t equals to 0, it will be a 0 vector. Okay. So gamma is not regular at t equals to 0. So gamma is not regular at t equals to 0. So t equals to 0 is a singular point of this gamma. So again, you can find the curvature of this gamma. So this is a planar curve. You can use the formula. So this curvature, you can find it to be 6 divided by 4 plus 9t square to the power 3 by 2. Okay, so I'll stop here. We'll continue in the next class.